Hi, my name is Jonathan Miranda, and I'll be covering the efficiency of a golf swing. The goal of this project is to first describe physical phenomena responsible for the kinetic energy of the club head in qualitative terms, and then quantify two products of the swing itself. First, quality of contact, which will be given by the coefficient of restitution, and speed, which will be given by the ball exit velocity. So moving into the physical phenomena of a golf swing, we have three physical phenomena involved in a golf swing: torque, centrifugal acceleration, double pendulum. In the context of golf, centrifugal acceleration is actually something else, but I'll get into that later. So first, torque is the rotational equivalent of linear force. Torque is created by a linear force applied on a lever arm that has a perpendicular component to the lever arm, which creates rotational motion around an axis of rotation. Centrifugal acceleration is uniform circular motion around a point of origin that has fixed velocity, acceleration, and radius scalars. And the double pendulum is a pendulum with another pendulum attached to it. So taking a deeper look into centrifugal acceleration, most golf physics videos will claim that there's centrifugal acceleration in a golf swing that is due to the club head rotating around the wrist. And this rotation around the wrist is due to gravity. So this is actually not centrifugal acceleration because there's first a lever arm, and second, there's not uniform circular motion. So due to the lever arm and this other force that's being applied to the mass on the lever arm, what's actually being described is gravitational torque, which is torque created by gravitational force that's applied to a mass at the end of a lever arm that's attached to a pivot that creates rotational motion of the mass in the lever arm around the pivot. And this gravitational torque is actually what's responsible for the rotational motion of the double pendulum. So when we describe torque during the golf swing, we have to simplify the model of the human skeleton to show lever arms that aren't readily visible. So first we have the pelvic girdle, and when the muscles that stabilize the pelvic girdle are contracted and sufficiently toned, we have a lever arm that's depicted by this horizontal bar here. And then similarly in the trunk, we have the ribs, clavicle, and the scapula. And when those muscle stabilizers are contracted and toned, we have what's effectively a lever arm that's depicted here. And then for the purposes of our model, we omit the elbow, and we consider the forearm and the upper arm to be one single lever arm that's shown here with the shoulder at one end and the wrist at the other. So when we look at torque in the golf swing, it's important to note that there are multiple torques that create rotational motion, which has mechanical energy that's transferred throughout the body into the club head. So we have torques that are generated in knee extension, hip rotation, shoulder rotation, and then the rotation of the arm around the shoulder, as well as wrist muscles that create torque that counteract gravitational torque during much of the downswing. So looking at empirical evidence for lower body torque generating a significant portion of the power in a golf swing, in Theodore Jorgensen's book, The Physics of Golf, he used stroboscopic technology to estimate that the power generated by a golf swing reaches a maximum of 2 horsepower, roughly 1,500 watts. Because a pound of muscle can only supply 1/8 horsepower, or 93 watts, and a given mass of muscle that produces motion in one direction must have an equal mass of muscle that produces motion in the opposite direction, there must be 32 pounds of muscle responsible for the power generated by the human body in this golf swing. 32 pounds of muscle will not be found in the upper body. However, it can be found in a combination of the lower body and the upper body. Next, we have gravitational torque, which is gravitational force applied to the club head and creates the rotational motion of the club head around the wrists. We then have the double pendulum effect, where the first pivot is the shoulder. We then have the first mass being the wrist, and the second mass being the club head. And what's important for the double pendulum effect in the context of golf is that it creates an efficient transfer of energy from the shoulders to the club head. So moving into the quantitative aspect of the project, we have the coefficient of restitution, which is a measure of the elasticity of a collision. A COR of 1 indicates a perfectly elastic collision, while 0 indicates perfectly inelastic. This is measured by the kinetic energy of a system before and after impact, where the kinetic energy is equal to 1/2 the mass times the velocity squared. The coefficient of restitution is then given by the sum of the kinetic energies of the system after impact divided by the sum of the kinetic energies of the system before impact. For the purposes of our experiment, the system is going to be considered the ball in the club head. Because the COR of club heads is regulated by the USGA and limited to 0.825, a perfect contact for the swing is going to be considered 0.825. Next, we are going to look at ball exit speed, because ball exit speed is responsible for, among other things, carry, or the distance off the tee. Carry is characterized by the horizontal displacement of the ball from point of impact to the first point of impact with the ground. And ball exit speed is going to be given by the velocity of the ball directly after impact. So many factors affect carry, such as spin, wind, air density, humidity, launch angle, exit speed. However, exit speed is the only variable that is controllable and non-optimizable, meaning that wind, air density, and humidity are not controllable by the golfer, and spin and launch angle are optimizable, but exit speed cannot be maximized. In fact, you want to increase exit speed as much as you can in order to increase your distance. So the PGA Tour average is 180 miles an hour, and exit speed is going to be given by the change in position divided by the change in time. We will then convert this exit speed into miles per hour so we can compare it to the PGA Tour average. Looking at the actual video of the experiment, what we did was we took the video frame by frame and placed markers for the club head, the wrist, the shoulder, and the ball. Each marker has a pixel X and Y component, and because we know the diameter of the golf ball in meters and pixels, we converted this pixel coordinate system into a meter coordinate system. So we can go through the golf swing frame by frame. And visualizing this graphically, we get our position diagram. So in green, we have the club head, in blue, we have the shoulder. In this turquoise color, we have the wrist, and then yellow is the ball. So looking at the results of the experiment, we have our implied coefficient of restitution that's given by the kinetic energies of the club head and the ball. We calculated the kinetic energy of these two by calculating the club head and ball velocity given by the position diagram, and the club head mass and ball mass, which were already known. Our implied coefficient of restitution was 0.8248, so a nearly perfect contact for the golf swing. And then for our ball exit speed, we have a ball velocity after impact at 68.6 meters per second converted to miles per hour, 153.5, so roughly 26.5 miles per hour less than the PGA Tour average.